All right, so let's get started. Welcome everyone to the HEP-TN Seminars. It's a great pleasure to kickstart the new year with the contagious energy and enthusiasm of Frank Verstraete. Today he'll be talking about quantum symmetries and tensor networks and what they have to do with conformal field theories, amongst maybe possibly other things. So Frank, please go ahead.
Okay, so thank you, Suki, for this invitation. This is indeed great, this new format of seminars that we don't have to travel. So even if we have a deadly disease, we can now participate in these meetings. So I would like to talk about some work that I have been doing with lots and lots of PhD students over the last years. So let me kind of mention the names of the key people. So Nick Bultink, Don Williamson, Burak Sahinoglu, and Michael Marian were the older generation of PhD students that kickstarted this whole project. The new PhD students are Robin van Hove, Laurens Lotens, and a postdoc, Romain Couvreur. And then, of course, there's also like the older, more senior people that were very much involved in the project, namely Yuto and Norbert. So basically, they taught me everything, and I will report on what they taught me. So this is a slide that I prepared for a grant application recently that was rejected. So I thought I can as well make use of it. It can be useful for something. So that's why I present this to you now, such that it was not a complete waste of time. Actually, Guy Vidal made that. What in this slide you see that basically the whole formalism of these tensor networks lives at the intersection of many different topics in physics, namely statistical mechanics. Quantum pH is more the quantum information entanglement. HEP-TH is more like the quantum field theory, and condensed matter physics is, of course, the physics of materials. And it turns out that these tensor networks provide some very natural language in which all of these concepts are very much entangled with each other. So please interrupt me whenever something is not clear or whenever you want to ask something. That's the great thing of these seminars online, I guess, that it's supposed to be much more intimate, which looks contradictory, but please interrupt me whenever you have a question. So the outline of my talk, I will briefly give a very generic introduction on tensor networks and symmetries. I hope most people are not bored by that, because most people that are subscribing to this seminars are probably already experts in tensor networks, but let me nevertheless repeat a few of the basic concepts there. So in the second part, I will we'll talk about NPO algebras, matrix product operator algebras, quantum symmetries, topological phases in 2+1D, so basically topological field theories. And then in the third section, I will kind of make the connection between topological field theory and conformal field theory through the use of some notion or a concept that is called strange correlators. And in the last part, if there is some time left, I will discuss some computational aspects of critical tensor networks. Okay, so there will be, between every of these sections, there will be, on request of Suki, there will be some blank slides in which you will be given some time to interact or to complain or whatever you feel like is necessary to make the talk more enjoyable. Okay, so let me go to the first part, just the very introduction of tensor networks. So tensor networks have a long history. The first really rigorous and systematic exploration of tensor networks started in '92 in combined, so kind of separate work from mathematical physics community and the DMRG community, the numerical physics community. And it turns out that they were studying exactly the same object. Then it took a while to understand basically why all these things work. This was basically mainly by combining the ideas of tensor networks with ideas of quantum information theory, and this led to generalizations like PEPs and MERA that probably you are all very familiar with. But the important thing is that the tensor network community has something like a mantra. Okay, so it means that the whole idea or the whole philosophy of tensor networks is that you can model the entanglement structure of many body wave functions using tensor networks. So these tensors basically they tell you how the entanglement is routed throughout your many body system, and therefore it leads to a very kind of interesting point of view, or a kind of a novel point of view of how to understand entanglement and certainly these correlations in the many body wave functions. And it's very much in spirit of Landau that somehow the symmetries, or the way these tensors that describe your system, the symmetries of these tensors are effectively describing in what phase you are. And if you have like a phase transition, this corresponds to symmetry breaking. And the great thing of these tensor networks is that they even allow you to see kind of symmetry breaking if you have things like topological order, for which there are no local order parameters. So it turns out that the symmetry breaking of the entanglement degrees of freedom is much richer than the symmetry breaking that you can see on the physical level, and therefore encompasses also many kind of notions of topological phase transitions. And that's certainly one of the reasons that these tensor networks are so interesting from the theoretical point of view. Okay, so what happens is that whenever you have a symmetry, a global symmetry in the system, then this global symmetry is reflected, as I just said, on the local symmetries of your tensor. So there's always, this is in many ways the whole idea of tensor networks is to map a global problem, a global wave function, to one and a single tensor. Okay, so this is especially true if you have translation invariants, then it's kind of simplifies things. But nevertheless, the main idea is that indeed local tensors describe the global wave functions. And it's very much like in mathematics, it's very much also like the spirit of category theory, you know, where you kind of have global structures and then this reflected into local equivalences, but these local equivalences can be much richer than the global equivalences. And that's basically exactly what is going on in tensor networks. So if you have like a global symmetry, these red dots that you see on this slide are basically local unity transformation that you do on your physical system. Well, this is equivalent to doing something on the edge of your kind of system. There's like an equivalent notion that acting on a physical system with the unitaries is equivalent to acting on the virtual system with an other kind of operator. And the whole idea is that this operator can be much richer than somehow the original kind of unitaries that you apply. So this is certainly best understood in the case of symmetry-protected topological phases. Some people also call it symmetry-protected trivial phases, but nevertheless, it's clear that this whole language of tensor networks shows you that there's something truly topological associated to these phases. Namely, you can associate a topological index to the different ways in which these representations are kind of implemented in the matrix product state. So here you see this is a local tensor, okay, like described in NPS. You have to think about an infinite line of these tensors. Then you have a local unitary acting on that tensor. And then there's something that is called the fundamental theorem of matrix product states, something that is actually kind of can be proven using just the Cauchy-Schwarz inequality. So it means that there must be a virtual action that is equivalent to the physical action. So what you have is if you act on the physical level with a unitary, there must be a virtual unitary, or it doesn't even have to be a unitary, but there must be a virtual action that is equivalent to this unitary. But the really interesting thing is that this virtual action does not have to kind of form a representation of the same group, because of course if you have a symmetry that must be associated to a group on the physical level. On the virtual level, this can actually be a projective representation. And the reason that it can be projective is that it always comes in pairs. So if you have some kind of a phase here, so if you multiply two of these representations and they are only equivalent up to a phase, this phase will cancel because they always come in pairs. Now, the interesting thing is that for a given group, certainly for finite groups, but also for Lie groups and so further, there's actually a very easy way of describing all possible projective representations, and they are classified by a discrete index. So given a certain group, it's very easy to figure out how many different ways are there to kind of get projective representations of that group in such a way that it's consistent, okay, that the associativity is satisfied and so further. And this associativity is effectively imposing some linear constraints on what these phases can be. And this, then at the end you solve some linear set of equations, and all the possible solutions of this linear set of equations gives you kind of the different indices that are associated to these different groups. So for a given group, there are many different, or depending, for some groups there are none, but for some groups there are many different projective representations. It turns out that for all these projective representations, you can actually find matrix product states that exactly transform according to that. And the whole idea is now that if you have two of these matrix product states that are transforming according to a different projective representation, and there's no way of interpolating these two states to each other while keeping the symmetry without basically breaking or without crossing a phase transition. And this has kind of been proven pretty rigorously, especially starting with the work of Chen Gu and Wen, and then also Norbert Schuch and collaborators. And so this is certainly one of the big successes of trying to understand symmetries in tensor networks. So the caveat, of course, of this argument is that it only works whenever your matrix product state is injective, which means that it has to be the unique ground state of a local gapped Hamiltonian. This is basically an if and only if situation. So, but that immediately leads to some very interesting insights. So namely that you can actually, it's easy to define symmetries that are incompatible with this injectivity. So for example, if you would have an SU2 and translation invariance at the same time for a spin 1/2 chain, then you can immediately see by trying to write this down as a translation invariant matrix product state that this is impossible. There is no way that you can write down an injective MPS that has both of these symmetries. So that immediately tells you that you have to break these symmetries. Okay? So you have to break the symmetry because you immediately see if it has to be SU2 invariant, all the tensors have basically to be Clebsch-Gordon coefficients. And if you kind of have a Clebsch-Gordon coefficient for which the physical leg is 1/2, then on the virtual level, you must either have 1/2 half integers on one side and integers on the other side. And therefore, this thing cannot be symmetric. You must have something like, you have to break your translational symmetry. And this is very interesting. This is, of course, exactly exactly the way that you open gaps. So the typical system for that is, of course, the Heisenberg antiferromagnetic ground state in the spin 1/2. We know that this ground state is critical, cannot be represented as an MPS, but nevertheless, the MPS will give you very, very good approximations. And what effectively DMRG will do is not simulate the Heisenberg model, but actually the Heisenberg model with a very slight kind of staggered a staggered kind of antiferromagnetic field. So it's basically giving rise to this Schuschriger-Haver, so SSH type of physics in which you basically break the translational symmetry. And this will be somehow the main theme. The reason that I'm saying this is that this is exactly kind of one of the main themes that we will kind of come back later, that we want to understand indeed what are the symmetries or what kind of topological, so there are some topological obstructions of writing down injective MPSs with symmetries like SU2 and translation invariance. And this is really why it either forces the systems to break the symmetry or actually to be critical. And this is the main theme of this talk, is trying to understand, at least to get some insights, is what, from the point of view of these tensor networks, forces systems, or what kind of symmetries forces critical chains or spin chains to become critical. And whenever you have a non-trivial kind of object, so in this particular case, you have a breaking of the symmetry, there's an immediate direct consequence for the excitations. And this will exactly also be the case like that in 2 dimensions, in topological phases, is that actually topological, somehow having non-trivial symmetries immediately goes hand in hand with non-trivial excitation. In this particular case, you immediately see that you can have a topological obstruction or a topological excitation in the system, namely a spin-on, in which you basically have either 2 half-integer or 2 integer spins on the virtual level. Okay, so that means that your elementary excitation would be a superposition of this green thing over all possible parts, and you can give it a momentum and all these kind of things. But what you immediately see is that this green object itself transforms according to a half integer. And therefore, there's no way of creating actually some object like that using local transformations. There's many kind of situations in which you can continue or kind of do the same thing. You can do a similar story for Kramer's theorem for time reversal. So if you have if you follow the Wigner description or prescription for time reversal, you have to basically take the conjugate of your wave function and multiply everything with sigma y if you have spin 1/2 systems. Then you immediately kind of, using the fundamental theorem, come to a conclusion that this is not compatible with an injective MPS. And that means that indeed you must have at least symmetry breaking, or it has to be critical. And this is exactly the content of this famous Kramer's theorem about time reversal. So there's many, many other cases that are interesting like that. There's actually another case that is, from the point of view of one-dimensional systems, that is extremely interesting. And this is whenever you have a system with super selection rules. Okay, so whenever you have a system with super selection rules, namely, well, of course, the simplest system with super selection rules is the fermion. Namely, you cannot have superpositions with an even and an odd number of fermions. Then from the point of view of tensor networks, you have to basically change or alter this whole notion of injectivity. So it's not because from the natural, from the naive point of view, your ground state wave function would be non-injective. So that means that you would have symmetry breaking, that nature can actually break that symmetry, because it might be that to break that symmetry, it would have to create unphysical systems. And this is exactly this situation for the Kitaev chain. And this was the, so of course from the technical point of view, what Kitaev did was very, very well known, but the really very ingenious idea of Kitaev to study somehow his Kitaev chain is to see that there is a topological abstraction, that namely the super selection rules kind of force this system to have a unique ground state, even if somehow the NPS that would describe it, and in this particular case, the NPS is actually a very simple one with one dimension too, looks like it could kind of exhibit symmetry breaking. And that's certainly also something that will come back later, somehow this whole notion that if you're non-injective, then a whole rich or new phenomena can exist. And it turns out, so this was worked out by mainly by my student Nick Bolting, who is now in Berkeley. Somehow there's a very nice way of understanding all of these symmetries in terms of these virtual degrees of freedom. Okay, so let's go to the two dimensions. So this was basically the introduction for things that are very well known. But let's try to go to the two-dimensional case, in which somehow we want to do this. We want to repeat this in the two-dimensional case, because of course the two-dimensional case is much richer than the one-dimensional case. So naively seen, you would think that if I have a PEPS tensor, so this is basically a tensor now that describes a whole system in 2D, that I can repeat the same story now, so that whenever I have a physical action on my, a physical symmetry, a global symmetry on my system, that this must be reflected by having some virtual degrees of freedom that transform according to somehow this, maybe a projective representation of your physical symmetry. Okay, but it turns out that this is not enough. It turns out that in PEPS, there's actually a more complicated situation that is possible. And this is exactly the ones that give rise to the really interesting kind of new physics that you have in 2D. Namely that these symmetries are not implemented by just tensor products of local unities, but they are actually implemented by a matrix product operator itself. Okay, so to kind of, you can rewrite this kind of thing by taking the inverses of these two unitaries, putting on the other side, and then seeing that basically if I have some object that I pull through my tensor, it has a physical action, and then it actually acts here on the virtual degrees of freedom. And if you would have something like a sphere, and you would start with such a bubble, a red bubble, and kind of grow it all the way around your sphere, you would see that indeed you would transform your state into one in which you have a unitary action on your full kind of system. So you see that this is indeed a sufficient condition. Having a symmetry like that, a local symmetry like that, is a sufficient condition for a global state to have somehow the unitary kind of symmetry. And this symmetry can indeed be implemented using non-trivial, a non-local operator. And that's the amazing thing, is that even if the action, the symmetry action on the physical level is local, on the virtual level, it can be completely non-local. And this will turn out to be the common theme in everything that we will say later. This is exactly the type of symmetries that will enforce systems to, like CFTs, to be critical. These are remnants basically of conformal symmetries, and this is what we are trying to explore now, but we are only kind of starting to understand the implications of these kind of things. Okay, so in general, this basically is a consequence of something that is called the fundamental theorem of PEPS, although there is no theorem like that. Nobody has really kind of proven these, except in under very stringent conditions. But it basically means that two PEPSes, if you define a PEPS wave function on a global, for any kind of lattice size using one and the same tensor, then these two states are equal to each other, even only if they are related by such a symmetry. Okay, so this is basically the equivalent of the fundamental theorem of matrix product states, although it's on less, from a mathematical point of view, it's on much less sure footing. Okay, so that means that these red kind of objects, they should, in the case of symmetries, of global symmetries, they should in one or the other way form representations of your symmetry. And if you kind of look at a finite group, okay, so for example, a finite group in which every one of these matrix product operators represents one kind of element of your symmetry group, if I multiply two of these NPOs, it should give rise to a new NPO, which is nothing more than the NPO that is corresponding to the group element that is the product of these two group elements. Okay, so these matrix product operators should form basically a closed algebra. They should themselves form a representation of your group algebra, or in this particular case, of course, it's a group. It's unique, so it's not an algebra. It's just if you multiply these two, it gives rise to a unique algebra. And now we play the game that is the typical game in tensor networks. You turn a global property into a local one. So if this product of two NPOs must be equal to one NPO, that means that there must exist, it follows from the fundamental theorem of matrix products, that there must exist something like an intertwiner that basically takes this lambda and mu, and if you pull this x through the lambda and mu, you get basically lambda mu. Okay, so there must exist an object like that. Then you can start deriving lots of kind of properties of this object. It has to kind of course, you can play the game with 3 of them, lambda, mu, and u, and then you have 2 different ways of doing this. These 2 different ways have to be compatible with each other. This leads to associativity conditions between these different intertwiners. And at the end, what you kind of get is the generalization of this 2 co-cycle, or this second cohomology group, to basically the 3rd cohomology group, which is exactly represented by pepsers that have kind of symmetries represented by matrix product operators. And whenever you have a non-trivial 3 co-cycle, this means that you will have indeed these non-local symmetries. Now, the great physical insight is that actually came from Xi Chen in a great paper in 2011, in which she derived basically, together of course with her collaborators, the whole notion of SPT phases in 2D. But the whole kind of the physical insight is that whenever you have basically a local Hamiltonian or a transfer matrix that has such a non-trivial matrix product operator symmetry, then basically, if you have a local Hamiltonian with such an NPO symmetry, it has to kind of, it cannot be a gapped system with a unique ground state. So there's only 2 possibilities. Either it has to be a critical system. So if you have a 1-dimensional Hamiltonian with such an NPO symmetry, it has to be either critical or symmetry broken. The way she proved that is by basically understanding that it is impossible to write down an injective MPS with an NPO symmetry. There's an inconsistency. There's a topological obstruction for an injective MPS to have an NPO symmetry. And that has a very strong consequence for somehow the entanglement spectra of these critical or of these states that exhibit topological order. It actually immediately means that all the entanglement Hamiltonians, and actually also the entanglement Hamiltonians that describe your or the entanglement spectrum that describes the eigenvalues if you cut your 2-dimensional system into 2 pieces, this basically has to correspond to the spectrum of a critical system. And that's indeed something that was already well understood in the condensed matter community, especially in the community of quantum Hall systems. And this is basically the tensor network analog of this. And of course, there's also lots of connections with things that people understood in topological field theory, kind of Witten's theorems that relate topological field theories to CFTs, and we will come back to this later because there's much more explicit ways of doing this. Okay, so let's give me a very simple example. So the simplest state, or the simplest Hamiltonian that has a ground state that is in non-trivial SPT phase is this famous CZX model that Xi Chen introduced, and it's the ground state of a frustration-free model. In some sense, in that sense, the entanglement Hamiltonian is completely trivial because it is really kind of gapped. Well, the system has 0 correlation length. Nevertheless, the entanglement Hamiltonian is just you cannot see the entanglement spectrum as being critical because it's actually the entanglement. So it's a terminal state of a critical Hamiltonian at 0 temperature. So sorry, at infinite temperature. So it just kind of cares about the support. And therefore, you basically have to do a small perturbation. So whenever you perturb that system slightly, you write down the PEPs that corresponds to this model of CCX, and you look at somehow the entanglement spectrum, you immediately see all the data of a critical theory. So this is really kind of a very strong evidence that indeed this is exactly like this. And the reason that indeed this entanglement spectrum, just doing a slight perturbation on the CCX model that generates a finite correlation length, the entanglement spectrum becomes really, falls into towers, and you can start studying all these kind of things, and you can start seeing that indeed the central charge is equal to 1. It's basically a compactified boson with radius equal to 2. So I was actually requested to include a few blank slides. So maybe this is a good moment to stop, because in the next slides I will kind of go further and talk about these NPO algebras when I'm not talking about physical symmetries, but purely on topological kind of symmetries. So maybe I can ask, I can pose some questions. If anybody has comments or questions, please, now is a good time to ask. Suki, nobody seems to have questions.
Yeah, so I think it's all clear so far.
Okay, let me continue then. Okay, so what we saw is in the 1D case that when going from the injective to the non-injective case, namely in the case of Majorana fermions, suddenly we had truly topological phases of matter. Okay, so that was not just protected by a global symmetry, but by writing down tensor networks that were not injective, we got kind of phases of matter that are truly topological, and there is no way, there's no single perturbation that can actually destroy the topology unless somehow the perturbation is strong enough. And this is the situation that somehow is very clear also in this two-dimensional kind of description in terms of matrix product operators. Okay, so just as in the case of this MPS, we can relax the requirement of this injectivity and define somehow the group elements as sum of the injective NPOs. So we say that actually the symmetry on the virtual level is not just, well, there is no physical action anymore whatsoever. It's just that somehow there's my PEPS tensors become non-injective. Okay, so basically you want to find larger classes of matrix product operator algebra. So you can start grouping them. For example, you can say, well, instead of kind of, if there's no physical group action associated anyway with my symmetries on the virtual level, I can as well kind of have that the product of these two is not giving rise to a unique kind of new NPO, but to a sum of NPOs. And it turns out that doing this is exactly kind of turns out that is equivalent to doing the representation theory of tensor fusion or of spherical tensor fusion categories. So these NPOs, and this is well, seems to be these NPOs at the end. We don't need any advanced mathematics to work with them. No? So the only thing we needed is basically this fundamental theorem turned out to give rise to this whole very rich and beautiful framework of tensor fusion categories. So, for example, in the case of the Ising model, what you will see is that the critical Ising model, or actually the Ising string net, which is the topological version of it, there will be two of these. There will be three symmetries. There's one symmetry that's called O sigma, and if you multiply these NPOs with each other, you get a sum of two other NPOs, a 1 NPO and a psi NPO, and a psi NPO is basically the spin flip. And this O sigma turns out to be the Kramers Wannier duality. Okay, and so anyway, so there is a whole framework in which we get kind of new NPOs. Okay? And so these topological phases are exactly now obtained whenever you write down PEPS wave functions for which this red line, if you pull it through the tensor, does not have any physical action anymore. So it's a purely virtual action, and it's a purely virtual symmetry. It's really the generalization of this Z2 graded kind of case of Majorana fermions in 1D to 2D, namely in which somehow your tensors themselves get non-trivial symmetries. But you see that whenever you have a PEPS tensor that has such a non-trivial symmetry, this immediately has consequences for things like the entanglement spectrum. Okay? This means that actually if you look at a certain region and you kind of look at what is the entanglement entropy of this region, well, you can calculate this by actually going to the virtual level. But this virtual level, you know that it has a symmetry. Now, if I kind of take a whole circle around this virtual level, it has to be equal to the original one. That means that somehow this whole, on the virtual level, your system only has support on a subsystem, namely on a symmetric subsystem of the whole system. So that means that the entanglement entropy will be less than you would have if you don't have the symmetry. And this turns out, you can actually characterize this very precisely, and it turns out that this is completely equivalent to this very famous and beautiful kind of notion of the topological entanglement entropy of Kitaev and Preskill and Levin and Wen. So let me kind of go a little bit deeper now into the features or the properties that these matrix product operators have to satisfy. But at the end, the idea is simple. There is some kind of a local way. The local tensors satisfy a pulling through equation with matrix product operators. Well, these matrix product operators must satisfy lots of consistency equations. Just like the case of symmetry protected phases, this associativity led to basically this the third cohomology group, well, here somehow we will kind of get some kind of the whole formalism of tensor fusion categories. So what we need is that indeed, whenever we have an NPO symmetry, we don't want to have infinite NPO symmetries. We want to have a limited set of NPOs. And that means if I have a symmetry or if I have an algebra, so they have to form a closed algebra. So whenever I have a certain matrix product operator A and a certain matrix product operator B, if I multiply them, they have to give rise to sums of other symmetries. And only by having somehow a finite number of a closed algebra will you be able to write down a system with a finite number of these symmetries, okay? Because these are the most, turns out to be the most interesting kind of cases. Okay? And now we can use exactly, again, this fundamental theorem of matrix product states to analyze somehow the consequences. If I have two NPOs that satisfy this, then there must be an intertwiner that will map these things to this, and you can start kind of writing down all the possible equations. And if you do this systematically in terms of these NPOs, you get basically a whole bunch of equations that that we have been analyzing in the last kind of 7 or 8 years. These are pictures that were recently made by Lawrence Lotus, because somehow they clearly kind of they are really minimalistic expressions of what these things are. So these black kind of things, this would be the PEP tensor. So there is actually a non-trivial tensor here, and this red line would be the NPO symmetry. So this pulling through equation of the NPO would tells you that if I have this NPO here, this is equivalent to this. So this picture is the same picture as we have already seen many times. So the fact that the product of two NPOs is equal to the sum of single NPOs is kind of reflected in this picture. So there must be a fusion. There must be basically a zipper equation. This is a tensor that would fuse these two NPOs to a single NPO. And basically I can pull this tensor through, and that's, so there's a local way of expressing indeed that two NPOs, the product of two NPOs is equal to a sum of single NPOs. Now these tensors, these fusion tensors must satisfy some associativity. So there's some kind of a non-trivial scalar that I can associate to these fusion tensors, and we call this F. And this object himself, it's very easy by kind of writing down and drawing lots of pictures that this F itself must satisfy some non-trivial consistency equation, and this is called the Pentagon equation. So you see that by just requiring somehow this MPS or this MPO formalism to be consistent, you immediately arrive at something like the Pentagon equation. Okay, this F symbol. So these these numbers are scalars that satisfy a non-trivial equation that has to be, that is related to the consistency of fusing two of these MPOs together. Actually, there's another kind of very natural condition that we want to impose on these tensors, which is basically the invariance under partner move. So whenever I have at the end my tensor network, this, of course, we are going very much into the direction of these quantum doubles, but also the string nets. We want basically these wave functions that we describe to be topological, and therefore there should be some kind of ways of describing these systems, that there's a unitary transformation that basically makes the geometry in which this kind of these systems are defined irrelevant. So there must be kind of simple ways of transforming your network in an equivalent way, and this is actually another kind of equation that we can impose. You don't really have to impose it, but it's a very natural condition that you impose. But anyway, if you do all of this, what you see is that this whole system of matrix product operator algebras leads to 6 coupled equations. Okay, so basically what you get is a system of 6 coupled equations for all different kind of scalars. Okay, so this is an F0. It turns out that this object here, this intertwiner or this fusion tensor, you can associate to something that we call an F1. And the product of two F1s must be related like this, using this F0 that satisfies the Pentagon. This F1 now we can associate a matrix product operator. This is this object, which is related or kind of defined by the F2. And there's this consistency equation, namely this zipper equation that it has to be satisfied. This basically gives a meaning of this F2. And the F2 must be able to kind of, which is the NPO symmetry, will be able to pull it through the tensor, the PEP tensor. And this defines basically the PEP tensors that you can have. This is F3. And then at the end, this PEP tensor itself has to satisfy kind of some non-trivial equation, which is also a Pentagon equations. And these 6 coupled Pentagon equations, they are actually called the big Pentagon in the Hopf algebra theory. Okay, and there turns out, and this is something that was we only kind of understood this very, very recently, or at least Lawrence Lotus understood this very recently, is that these equations are completely equivalent to the equations of bimodules. This was actually suggested to us by Dominic Williamson. So what it tells you is that if you look at all these equations, or let's say look at these equations, so it basically relates the symmetries. somehow of your NPO symmetries to the physical tensors. Okay, so this is exactly this red kind of things are the NPO symmetries. These black kind of things are the PEPS tensors. And what this big pentagon tells you is that these two things have to be kind of related to each other. They have to be Morita equivalent. Okay? And that turns out that this is somehow the content of this big pentagon equation. So it tells you that you can describe a physical theory that has a certain kind of anionic content by a virtual theory. And you can do this in many different ways, but all the different ways in which the virtual theory will be related to the physical theory is in such a way that they are Morita equivalent. And Morita equivalent actually means that they have basically the same topological sectors, that they have the same anions and all these kind of different ways. So this is a beautiful connection between basically the virtual degrees of freedom or the virtual way of describing a topological theory. Well, it turns out that these things, not surprisingly, have to be very much related. And I will come back somehow to these Morita equivalents.
Frank, I have a question.
Yes.
So could you, I kind of missed what these different Fs are. Could you explain the previous slide again? Are they each by F1, F2, F3, so on? Do you mean they are independent 6J symbols?
Well, at the end, in principle, we don't know what they are. Okay, so this F is just F0 is a scalar. This F1 is this matrix product is the intertwiner for a matrix product operator. Okay, so this is basically this F1 is this one here.
Okay.
The F2 is basically a notation. It's just a scalar equation for this. So what we write down here is all. So these equations have to be satisfied independent of what the legs are. No? So you can put some numbers here: A, B, C, D, E, and you can sum. So for example, here will typically be a loop. So this equation is just an equation that tells you that, well, this is a tensor network kind of diagram, and you can relate basically this. Well, this is a pictorial way of writing down kind of an algebraic equation that basically defines F2. Okay, so what you see is that by this line of thought, the different F symbols are defined. You start with F0, then you look for all F1s that relate to this F0. And typically, well, this is what I wanted to say here. There's there's different solutions. It turns out that there is one way of associating to all these tensors just all the same kind of F symbols, namely the somehow the solution of the Pentagon equation. And this is exactly what gives rise to this Leven-Wen string nets. But there's also other kind of ways. So this F0 is very similar to what you mean by a 6J symbol. Okay? So this is what you see is that this is a kind of a recoupling of two kind of Clebsch-Gordon coefficients. Okay, so and this F0 is indeed the 6J symbol associated. So if the tensor fusion category would indeed be the one that is correlated to the EREPs of a certain group, then indeed somehow this F0 would be the 6J symbol for that group. So it means that actually these red things can as well be Clebsch-Gordon coefficients. And this is a completely different, solution, namely in which we take the F0 to be the 6J, the F1 to be the 3J, and then the F2 will be an NPO, the F3 will be a possibly different 3J, and the F4 again a 6J. Okay? And the only requirement is that this F4 and this F0 are Morita equivalent. And this turns out to be exactly the case when you describe basically topological phases of matter in terms of quantum groups. Then indeed you will have these 3Js. But there's another option, namely choosing all these Fs equal to each other. And this is exactly when you get somehow these Leven-Wen string nets. Okay, so what does it mean to be Morita equivalent and having all these kind of properties?
Just one more question about the previous slide. So what do you mean by these are equations for bimodules? Can you say just briefly, what does that mean?
Well, so there's a huge literature on category theory and tensor fusion categories, and a very important topic there that was originally, I think, discovered by Ogneanu, but then expanded by many other people, is a notion of bimodules. And a bimodule is basically some intertwiner between different categories. And there's lots of consistency equations needed for having this. And it turns out that whenever you have two different topological or two different categories that have basically the same Drinfeld center, and I will kind of come back to this later, then there exists a non-trivial intertwiner that basically maps all the content of one theory to the other one. So this is exactly what, for example, would happen between, well, this a very simplistic kind of case of that would be like you can describe topological, you can describe like gauge theories like quantum doubles using the string net picture and using the quantum double picture. And then there would be like an intertwiner, a bimodule that relates these kind of different theories to each other. That's a very simple case. And people like Itaiv and Kong, they have kind of worked this out completely. This is actually also very much related to the boundaries of topological theories. People have understood how kind of to do this, and you kind of write down a whole set of equations that do not look at all like these equations, but for one other magical reason turns out to be completely equivalent to these equations. Okay? And this is, so that means that we know that because of that work of this category people, we know that basically this F0 and this F4 have to kind of be correspond to categories that are Morita equivalent. Namely, they will have the same, the anions in the theory or the topological sectors in the theory will have to be the same. And that's the only requirement. And whenever this is like that, you will be able to find solutions of these PEPSs. And this is very new work in which we need to understand now what is the relation between the virtual and the physical degrees of freedom. So this work here to relate when all these things are equal, this was exactly the work that was done by Nick Bultink, Michael Marian, Dominic Williamson, and other PhD students like 5 years ago. This is what we kind of did. But now we understand that there's actually a much more general way of understanding this in terms of these big Pentagon equations. Okay, so what does it mean that two theories are basically these Morita equivalent? It means that basically their topological feature or the ground state manifold or somehow the feature or the topological spins of their anions and all these kind of things in the theory will be equivalent. Okay, so and this NPO business allows you to, in a very concise way, to understand all the different ground states. So if you have like your TFT or you kind of have your spin system defined on a torus, it's clear how to kind of create new ground states. So if you have a PEPS that has all these NPO symmetries, it's easy to write down PEPSs that are actually orthogonal to the original one that are nevertheless also in the ground state. And the reason that this is trivial is that these NPOs are completely invisible. The whole property of these NPOs is that you can pull them through the lattice, you cannot see where they are, and therefore putting an NPO somewhere cannot have any effect on the energy because the energy is only dependent on the local expectation values. So putting NPOs there, you cannot see it. But the problem is you have a torus and you have an NPO, they have to cross at some point, these two NPOs, and you have to resolve this crossing. And this resolving of the crossing turns out to be, well, kind of new kind of NPO algebra that is a little bit richer than the original one. And this kind of in the category slang, this is actually what is called the output category. So the input category is basically the fusion rules of your NPOs, just the single NPOs. And the output category is basically the objects that you obtain by merging, or kind of when two of these NPOs cross, and that will give rise to the topological sectors in your theory. So as a very simple example, take the toric code. There's two of these NPOs, namely just the identity and a product of sigma x's. But whenever they cross, you kind of get four of them. Okay, so the input category is Z2. The output category is actually the one that has four different kind of ground states and actually also will have four different types of anions, as everybody kind of knows. It turns out that all of this has a very concise and natural description in terms of matrix product operator algebras, where these gray things are just the fusion tensors and these red things is just a normal NPO. What you see is that this object is basically, well, this red line here, this red circle is, for example, this one here. And turns out that this thing itself forms a closed algebra. So if you kind of have an object like this, it has like 5 indices on the outside, it has 5 indices on the inside. So you can multiply objects like that with each other. And it turns out that this forms a C-star algebra. So if you multiply 2 of them, you can again write it as a sum of kind of objects like this. And then a very natural kind of case to define the different grounds, it would be, well, what happens, can I decompose this algebra or all these objects that I can put there into kind of a direct sum of orthogonal states? And this is exactly what was done then by Nick Bultink and my other students. They realized that in terms of these tensor networks, what you have to find is the idempotence of this enlarged NPO algebra. And it turns out that this is completely equivalent to what people already did long before in the field of tensor fusion category. Namely, this is constructing the Drinfeld center or the Ogniano's tube algebra of the input category. But the nice thing is that these NPOs, this has a very natural description in terms of NPOs. And of course, you can now define basically all the possible ground states for any kind of topological theory on any possible genus. Okay, so you can make as many holes as you want. You draw just as many of these NPOs that you want. Whenever they cross, you put one of these tubes. And of course, if you put one of these and you would put another kind of thing here, you will be able to multiply them, because that's the whole point of this algebra. So they form kind of a closed algebra, and this is indeed the topological. This defines completed topological sectors in your theory. It turns out that these idempotents give rise to the minimally entangled states in your topological phase. Okay, but the beautiful thing is that exactly the same object, namely these topological sectors, also completely defines all the onions in your theory. Okay, and of course, I'm kind of running a little bit forward now. This will, of course, correspond also to the primary fields in your CFT. They will turn out to be exactly expressible in terms of these same tubes or these same idempotents. Whenever you have an idempotent like that, you put it somewhere, and you have the string associated or attached to it. The string is invisible. Sorry, the string is invisible in the thing. It has to end somewhere, and these are the two onions these are the elementary excitations in your kind of your theory. They're completely described by exactly the same topological sectors. Okay, and you can do this actually for any possible category, input category. Do this like for the Ising case that we discussed before. You see, well, there's basically 9 idempotents, and all these different idempotents basically define the different topological sectors in your theory. So in the case of Ising, actually, there are even analytical ways of doing this, because the input category is modular, but somehow this whole idempotent business is even true whenever your input category is not modular, and somehow the output category is always modular. And this is exactly the whole notion of this Drinfeld center, that for every input category, even the non-modular ones, the output category has well-defined onions that have well-defined braiding and has well-defined all the kind of possible properties that you want. From our point of view, of course, this NPO business is just rephrasing things that were known a long time ago already in the field of topological, of gauge theories in terms of tensor fusion category. Of course, also the papers of Kitaev were extremely influential in kind of bringing all this extremely difficult math towards somehow the condensed matter community. But nevertheless, these NPOs give an extremely kind of concise and simple way of understanding this. So for example, what is the topological spin of an onion? So an onion, you take one of these sectors, put it somewhere there, and the topological spin of an onion is basically what happens if I rotate that onion over 360 degrees. Okay, so there's a string attached to this onion. Rotating this over 360 degrees is basically winding this string again around the onion. But this, as you see, is nothing more than basically the product of 2 of these tubes. Therefore, it is expressible as a sum of tubes, and it turns out that in this particular case, just equal to the original one up to a phase. Well, this is the topological phase of your onion. And if you do this for the toric code, you see that this phase is kind of for, there's 4 different excitations, is 4 times kind of 0, but for the fermion, it is exactly pi. This is indeed, well, just expressible. So the non-trivial statistics is really, from the point of view of these tensor networks, is completely due to the fact that there are non-local or non-trivial strings associated to these objects. So there's some kind of a string that is invisible on the physical level, but is living on the entanglement of degrees of freedom that kind of forces the statistics of these particles to be non-trivial. Okay, so you can also do, of course, you can play exactly the same games that people kind of have played a long time, like what are the S and T matrices. So people typically say, well, you take a torus, you cut it. So for example, for a Dane twist, and you kind of twist it and glue it again to each other. This is kind of very strange for a lattice system. No, you cannot just do this. You cannot compare the original system to the new system when you kind of twisted the thing, because your Hilbert space is just completely different. So, but from the point of view of these NPOs, what you do is just kind of bind the NPO around the torus and say, well, how do I relate this again if I have a certain idempotent or a certain topological sector? And I take one of these NPOs, wind it around it like this. How can I compare this to the original kind of tube algebra? And this is exactly the T matrix. You can do the same thing with the S matrix, and all these kind of things work out in a beautiful way. So it's all about NPO symmetry. So these different topological sectors are really kind of giving you the different possible ground states. Of course, the crucial property, and this is one of the main reasons that people are so interested in all these topological theories, is that they allow you to do non-trivial quantum computation. That whenever you have anions, you would be able to do topological quantum computation for which the errors are basically protected by, because everything you do is topological. And for this, what you need to do is, if you have an anion, for example, this red anion here, and you have another anion, and this blue string is some string associated or attached to another anion, you would like to basically pull this string through this anion. And what you see, well, you can do this again with the tube. And what is happening is actually that the content of this anion is teleported using this tube do somehow the crossing. And that means that this blue string, you can just relate this, well, this thing will be changed, and then you have a crossing between these kind of two things. And if you play this game in using these tensor networks, you see that whenever you would have onions and you would start braiding them on the lattice, so you take one of these string nets, take these elementary excitations and start moving them and crossing them over each other. Whenever they cross, you have to put one of these idempotents there. And these idempotents turn out, well, actually it's not an idempotent, it's something that lives in this algebra of these cubes. Turns out that this, this defines a unitary transformation on the virtual degrees of freedom. And in a beautiful kind of way, in the sense that by understanding basically the action on the virtual level of kind of braiding of onions, you see that what you're actually doing is nothing more than a unitary circuit on the virtual degrees of freedom. And this kind of gives you a very nice link between this whole idea of topological quantum computation and the normal quantum circuit model. So if you do topological quantum computation and you would describe it using the formalism of tensor networks, what you would actually do is nothing more than a quantum circuit calculation on the virtual entanglement degrees of freedom. Okay, so let me, this is all I wanted to say about topological order and topologically ordered systems in 2D. So now I would actually like to make the step to conformal field theory. So Suki, how much time do I have left?
So maybe 10 or 12 minutes.
Okay, I will have to hurry up then, but I will, okay, because I'm only on the third part here. Okay, so now it turns out that there's a very kind of nice and natural connection between topological field theories and conformal field theories. So people all know this, okay, since the work of Witten and Jones and many other kind of geniuses, people have understood this, that all these things are very connected. Now, the amazing thing is that using tensor networks, the same tensor network can both describe a TFT and a CFT. You actually just have to change your perspective, but it's exactly the same. It's really the same tensor network, and it's the same symmetries that emerge. So this the main technical kind of idea was obtained by looking at the paper of Yu and Xankik Xu and collaborators in a concept that they call the strange correlate. Okay, so their motivation was to try to kind of find some way of detecting non-trivial SPT phases. But at the end, what they did is take kind of a wave function in a 2+1 dimensional theory. You're in a gap phase, in a topological phase, and you take the overlap of that wave function with the product state. And then they realized that whenever this product state, somehow this is a part, you can understand now this thing as a partition function of a classical stat-mech model. And if this partition function of the classical stat-mech model is critical, then there's a good kind of there's a very good kind of reason to think that the original theory was topological. Yeah, and indeed, somehow the reason of that is of course that whenever you start with a theory that is topological, it will have non-trivial NPO symmetries. You take the product, so basically you take one of these tensors here, and you take somehow this is a tensor network. You take a product of all these physical legs. You just take the overlap with the product state. This is the partition function of a stat-mech model. But that stat-mech model, which is described now by, well, this partition function, has this non-trivial NPO symmetry. And then we have this Xi-Chan's theorem that tells you that whenever you have a stat-mech model or a local quantum Hamiltonian in 1D, this is basically one is just the exponential of the other one, then this kind of stat-mech model has to be critical. Okay? And this is basically something like a Liebschutz-Mattis type of argument, no? That whenever you have a non-trivial NPO symmetry, you have to be critical or symmetry broken. Okay, and that's these are the only two possibilities, and this is exactly the link. These symmetries, these non-local NPO symmetries, are exactly the objects that force this system to be critical. So we can do this. This is the same example as we did before. Take the CZX model, take the overlap with the product state, and you immediately see that basically a critical model emerges. Okay, so that means that actually the criticality, somehow these NPOs seem to protect your stat-mech model or your quantum Hamiltonian towards any perturbation that would open a gap. Okay, so that means that these are non-local symmetries, and of course these are really the generalizations of Kramers-Wanier type of arguments. No? So everybody knows that this Kramers-Wanier duality is exactly the one that forces the system to be critical, and these NPOs generalize this to a much broader kind of class of systems. It tells you that whenever you have indeed an NPO symmetry, that basically whatever perturbation that you can add to your Hamiltonian that still commutes with this NPO, you will not be able to open a gap. Okay, and this is an extreme kind of simple microscopic implementation of this idea on the lattice. So it turns out that, of course, in the context of quantum field theory, people know this, but this is really a lattice kind of remnant of all these symmetries, and it can really be understood. So there's a whole series of extremely interesting papers by Jürgen Fuchs, Runkel Schweigert, and also many other collaborators. And it seems that actually what we have been doing here is very much like the representation theory of many of the ideas that they kind of already kind of envisioned. Of course, they did also kind of more. They look at more general categories like Reshetikhin kind of derived categories that for which we have no idea how to do this using our formalism. So this work that we do is also very much related to work of David Eisen, Mong, and Paul Fendley, in which they kind of basically construct classical systems, spin systems, critical spin systems using concepts of tensor fusion category, and all of these. Well, it's not surprising that all of these different angles are, of course, or all these, although technically they are different. That at the end the mathematics all boils down to this tensor fusion category. Okay, so basically what this is basically the state of the art. No? So this whole connection between TFTs and CFTs was pioneered by Witten in his very famous papers in the 80s, in which he kind of looked at Chern-Simon's theory, and then at the edge you will have anomalies, you have CFTs that basically describe all this. This gives you a direct connection between CFTs and TFTs, but of course there it's not entirely clear that these tensor, you don't have an immediate kind of mapping from one to the other. So then people like Turaev and collaborators and more, Seiberg, Fuchs, Runkel, Schweigert, they understood that there's a deeper, that the right mathematical framework for describing these things is this modular tensor fusion category. And then Kitaev and Evan Wen, they made use of this to create all these states that have topological order. It turns out that exactly the same data was already used somehow also kind of quickly after the appearance of these papers to construct critical spin systems in 1D. These are these so-called anionic spin chains, like this golden chain, and this gives these critical spin systems. And it turns out now that this strange correlator kind of is making a direct connection between this whole notion of topological order and critical spin systems. Now, it really kind of tells you that whenever you have a system with topological order, by taking the overlap with the product state, you basically create a critical spin system that has exactly the same symmetries as somehow this topological order. And if these symmetries are non-local, this NPO algebra is non-trivial, or you have a non-trivial realization of this NPO algebra, then indeed somehow this is exactly what protects this system or forces this system to be critical. So this is basically somehow a Lipschutz-Mattis type of argument for matrix product operators. Whenever you have a local quantum Hamiltonian that commutes with a non-trivial NPO algebra, and the system does not exhibit symmetry breaking, then it has to be critical. Okay, so as I already said, this NPO symmetry excludes relevant perturbations. And the way you prove this is again using somehow this whole idea of the fundamental theorem of NPS. And just to give you an idea, if you do this for the Ising string net, the NPOs that kind of generate the Ising string net, and you try to find what is the local Hamiltonian that commutes with this NPO, what you see is that this is exactly the critical Ising model in transverse magnetic field. Okay, so this is the only Hamiltonian, and whenever you would add perturbations now to the Ising model by maybe some longer range that commute with this NPO, you will not be able to open a gap. So that means that these NPOs, these matrix product operators, are basically the lattice remnants of well, they protect your system. They are the ones that tell you that your system is critical and you will not be able to open a gap. So the first kind of system for which we tried this out was like the Fibonacci string net, because this is certainly from the technical and numerical point of view the simplest one, because it has the smallest bond dimension. You do this, you take the Fibonacci string net, take the overlap basically with the product state, and what you get is exactly the critical hard hexagon model, the very famous one that was studied by Baxter, that is critical, and it has all these NPO symmetries. You can kind of study the towers, the characters, all of these kind of things. And actually, you can also do this, of course, for the non-unitary CFT, and it turns out Lawrence Lotens did this. You can actually, all the IDs and all the towers, everything kind of goes through in a very similar way. There is actually one very important caveat. This actually, the model that you get by taking this projector, okay, by projecting your PEPS tensors on a product state, is not equivalent to the hard hexagon model in the sense that you get negative signs. But the number of negative signs is always kind of canceling each other because they come in pairs. And it's very important to have these negative signs, because only when your tensors exhibit these negative signs will you have this NPO algebra. So that means that actually the natural way of defining these RSOS models that are critical, indeed they are equivalent somehow to the models that we will describe or obtain using the string nets, but nevertheless there are always negative signs and phases that you will need, but that will of course have no influence whatsoever on the real partition function, because they always cancel because somehow topological reasons that they will always come in pairs or in triples and so further. Okay, so what you can do now is trying to systematically explore now what the connections is. So in the topological phase, we understood what onions were. They were defined by these idempotents with a string attached to them. Well, what happens now with what is the analog of this in the CFT that is obtained by just projecting this thing down? Well, it turns out that this kind of topological sectors exactly define all the primary fields. So all the different towers that you get in your CFT are basically related to this kind of different, these are basically really the primary fields in your kind of CFT, and all the different sectors correspond to the different types of particles that you have. And there's a systematic way of understanding now what to put there. So given one or the other critical lattice system, using this NPO kind of language, we can actually find the exact local operator that will create somehow, that will have the highest overlap with somehow the really kind of conformal invariant primary field that is present in your theory. And you can do this by diagonalizing matrices and so further and so further. So what this is really somehow a systematic implementation of this, of a beautiful program that was started by Kadanoff and Seva, in which they wanted to understand basically what are the excitations in the kind of critical Ising model. No? So they constructed all these, well, this is an amazing paper actually written in the 70s. It's really kind of has many of the ideas of conformal field theory. This is long before conformal field theory is already present there. No? So they want to have this. So they construct basically elementary kind of excitations in the Ising model, and they see that there's domain walls between them that can be moved and so further and so further. Well, what these NPO algebras do is basically allow you to do this in a systematic way, and actually also for more general objects that have non-trivial strings attached to them, such as, for example, sigma strings. Okay, so indeed for the Ising model, while you have these objects that have no string attached to them, these are these idempotents of your algebra. Well, these are all the different onions, all the different primary fields that you can have. But now we can also construct directly kind of the primary fields that have kind of a Kramers-Wanier duality string attached to them. Again, you can start doing this for any of these critical RSOS models. You can actually do this for a much wider class. So all these RSOS models that are known to be in one-to-one correspondence with all minimal models, so all kind of CFTs with C smaller than 1, have somehow a lattice kind of realization in terms of RSOS models. This was first figured out, I think, in the PhD thesis of David Hughes. But anyway, so you can play this game and it works for all these kind of different cases. Okay, so you can also start kind of course, you can ask, why do you take an overlap of these string nets with the product state? Maybe I can take the overlap between 2 different string nets or 3 different ones if somehow there's a way of associating or connecting these different kind of input categories to each other. Well, it turns out that all these different ways correspond to like coset CFTs. You can also put non-trivial tubes in the partition function such that you only have overlap with certain kind of things. This turns out to be equivalent to orbifolding. So this is kind of the things that we are currently working out with our students to understand indeed, to basically find a dictionary between somehow this whole yellow book of CFTs and indeed what is somehow what are the remnants of this on the lattice. And one of the main reasons that we think this is very exciting is that this whole formalism, all these kind of ideas of conformal field theory that arise very naturally here, like these primary fields, these towers, topological sectors, spins, and so further. For building up this whole framework, we nowhere needed that the whole system was conformal invariant, because we were working with a lattice system, so there is no conformal invariance. And nevertheless, it is possible to kind of build up this whole framework. And this is, of course, very exciting because it might kind of suggest that we would be able to do something like that in higher dimensions. And one of the reasons that indeed people in the CFT community got so amazing mileage out of CFTs is that, of course, this whole fact that this is related to analytical functions, that there's this kind of accident that the Lie kind of the Lie algebra of analytic functions is equivalent to the Lie algebra of conformal maps. But somehow by all this kind of, if you look at the conformal field theory kind of literature, they always make use of this. Well, we didn't have to make use of this, and this makes it more kind of believable that we will be able to generalize this to higher dimensions. Okay, but things like critical exponents and all this, well, using this matrix product operator or this topological kind of ideas, it's clear that all these critical exponents are completely fixed by the topological order, by the input category. So to me, this was a real eye-opener, that somehow the fact that there's so few possible critical exponents in nature, so few observed, this really has to do with the fact that there's only so few kind of possible matrix product operators or tensor fusion categories. And basically, whenever you formulate, you say, okay, this will be the virtual symmetry of my theory, this completely fixes all the kind of possible critical exponents, the topological spins, everything is basically completely fixed by these solutions of the Pentagon equations. And to me, this was a real eye-opener, that this kind of gives much more, this gives a non-trivial insight into this whole notion of universality, mainly the fact that you can always bring this back to this kind of topological arguments. Okay, so of course you can also do the same thing for boundary CFTs, bind modules. So you will be able to kind of see this later. Okay, this is so I'm almost done. I think it's also almost time now to stop. But so basically the basic objects, and some of my students are working on this now, is trying to understand now what happens in 3D. Well, for this we meet basically not the fundamental theorem of PEPS would become something like a tetrahedral theorem, in which you kind of have Pepo symmetries that you can pull through the lattice and will give rise to criticality and so further. Okay, so this is the second stop, but I think this will be the final stop. So in some sense, in the rest of my talk, I wanted to talk a little bit about computational aspects. Or maybe if you give me 1 minute, I can give you a very, very small summary.
Yeah, please go ahead. Yeah, just take a few minutes.
Okay, so tensor networks. So what this whole business or this whole formalism shows you is that matrix product operators are crucial to understand, indeed, from the analytical point of view, all the criticality, okay, and obstructions to be gappable. Okay. Nevertheless, we know that matrix product states are extremely useful in simulating kind of critical systems. Okay. So what actually happens is that if you kind of use matrix product states, you're not really simulating the critical theory. What you're doing is kind of simulating a slight perturbation of the critical theory. Okay. So effectively, you're adding like something like a staggering magnetization or a staggering in your kind of Hamiltonian that opens a small gap. And that means that actually this whole idea of doing DMRG for critical systems, that the whole there's a whole kind of new way of simulating these things by understanding that entanglement is nothing more than another parameter in your theory that opens a gap. So simulating a theory with a finite amount of entanglement, somehow you have to. There's a systematic way of doing, somehow formulating finite entanglement scaling hypothesis. Okay? And turns out that there's still lots of opportunities and interesting things. This is really following up work that started by Tomotachi Nishino. Then Luca wrote a very influential paper. Patrick Frank Polman and company, they wrote very interesting papers. But it's only very recently, so this is a preprint that appeared like last year in our group. It shows you that actually there is a very systematic way of doing somehow data collapse. So by combining, you can actually combine results all of different dimensions. There is always a way of scaling all these methods and putting all the data that you do with different bond dimensions on top of each other, such that you get a kind of extremely nice kind of collapse. And doing this, you have kind of a way of systematically kind of exploring and extracting critical exponents. Okay, you can do the same thing for field theories, for lambda phi to the 4. You get kind of complete collapse for all possible kind of things. We also have kind of numerical kind of work that's going on now to try to understand the connection between the Mera and matrix product operators. I just refer you to somehow these papers. And I have to apologize that I went over time. So certainly these are kind of some of the relevant references if you want to kind of learn about these kind of matrix product operator algebras and connections between kind of CFTs, TFTs, also kind of notions, what are these kind of string nets, what is symmetry enhanced topological phases, twisted G-injectivity, and certainly also somehow these connections between TFTs and CFTs. Turns out that indeed, or kind of this whole formalism of matrix product operators provides a very systematic way of implementing this program that has been along since a very kind of long time. So thanks a lot for your attention, and I'm hoping that I get some good questions.
Okay, thanks, Frank. Are there any questions?
I would like to make one.
Yep, go ahead.
Hi, Frank, it's Luca. I have understood that if you have an MPO with this, sorry, if you have a PEPS with this MPO symmetry property, then necessarily you get this either critical or symmetry broken state. Is it the opposite true? So if you have a critical to the partition function, does it always need to have this MPO pulling through thing?
Well, so this is indeed an open question. So it feels very much that all these models that these MPO symmetries are very much tied to the notion of integrability. Okay, so because these are really the lattice models that have the local symmetry exactly implemented as a matrix product operator. So I could, of course, envision a system that I kind of start perturbing, that I have to basically start dressing the matrix product operator by some local quantum circuits that would kind of basically spread this thing out. Nevertheless, the claim would be that whenever you have a critical system, that indeed it would flow, it would be somehow in the same universality class as a system that has exactly these kind of symmetries. It might be hard to find this, but there have actually already been some works of extracting this, given somehow a numerical PEPs that you optimize, try to find indeed whether there are kind of matrix product operator symmetries. So there's current way going on in, forgot exactly the references to this, but there are people that are trying to study this, and it seems kind of to be very promising that you can actually extract approximate matrix product operator algebras, and out of this then you would be able to completely characterize all the critical exponents exactly. So this is also one of the kind of interesting kind of things now. If you look somehow at the meta wave functions, turns out that meta wave functions don't have that obstruction. It is actually possible, and this was done by, for example, Dominic Williamson and Jacob Bridgman. They constructed exact meta with non-trivial matrix product operator symmetries. And it has to be like that, of course, because we know that meta can encode critical systems exactly. So and then there's a, well, you can actually do this, and therefore you can write down meta that would have the exact critical exponents for the Ising model by imposing this non-trivial NPO symmetries, namely this Kramers one-year duality NPO. Then you would get a meta that would have the exact critical exponents that you need to have.
And Frank, can I just ask a simple follow-up to that? So this statement that if a state has an NPO symmetry, then it must necessarily be critical or symmetry broken. Is it has it been proved, or is it?
Yes. So the original the original idea is it's really a slight variation on the very ingenious idea of Xi Chen. So what she did is basically prove that an NPS that is injective cannot have an NPO symmetry. Okay, and this is actually just by some associativity and a few kind of, you get a contradiction in the case of, sorry, if the NPO corresponds to a non-trivial co-cycle. And you can do this explicitly. You can, because the fundamental theorem of NPS, you can know that there's intertwiners, and if you put all these intertwiners together, you see that there's some kind of an inconsistency, namely that this three-co-cycle you must be able to write down this three-co-cycle as a product of basically co-boundaries, which is clearly kind of completely impossible. So and this is the original argument of Xi Chen. So the more general kind of arguments are a bit more involved, but using somehow this fundamental theorem of PEPs and so further, you can actually prove this. And we will include somehow a proof of this in a review article that should be out in the next coming weeks. That is written together with David Perez Garcia, Ignacio Sirac, and Norbert Schuch. So we are kind of writing down a big review article on all the possible ways in which you can understand the fundamental theorem and its applications, and also connections to topological order, to SPT phases, to RG fixed points, and all these kind of things. So this review article should be on the archive, hopefully in the next 2 or 3 weeks.
Okay, thanks. Are there any other questions? If not, let's thank Frank again. All right, so I'm just going to stop the recording.
Yeah.
And yeah, thanks, and see you next time.
Yeah, thanks a lot.